Hi guys, hope you're having a great day. So let's take a look at 2.2, which is change in linear and exponential functions. Let me share my screen, that would help. All right, so we talked about last video that something called arithmetic sequences, where you're adding a common difference every time, and something called geometric sequences, where you're multiplying by a common ratio every time. I would take a minute and pause it and read through this. This is important. So I mentioned in the video that you've probably thought of a linear function as adding the same common difference every time, okay? And a geometric as kind of like an exponential. So there is that relationship there. The important kind of distinction is a sequence is a list of numbers, and they can be represented by linear functions. However, a sequence is going to be what we call discrete, meaning that it happens at certain values, okay? And a linear function and an exponential function are something we call continuous, meaning like I draw a line with a straight line without picking up my pencil. It exists everywhere. When x is 0.12758, there's a value of y that exists there. Okay, so important difference between discrete and continuous. Sequences are discrete, linear and exponential functions are continuous, but we can model the pattern with linear and exponential functions. All right, so let's start with just example 1. So we're going to start again with arithmetic and move our way to geometric. So I can see right here, okay, this sequence that's given to me, 1, -5, that's already filled in the table, 2, -3, 3, -1, 4, 1, 5, 3, 6, 5, and I don't think this one is plotted for you, but it should be down there at -7. And so I notice here looking at this, and hopefully you see as well, that I'm adding 2. That is my common difference every time. So D would equal 2. So just from what we did before, A sub n would equal, and it depends how you write this, but -5 plus 2 to the n minus 1. Okay. So if I was going to look at this, you could have also said A sub n equals -7 plus 2n. Okay, if you started with the 0th term, you wouldn't have that n minus 1 component. All right, so essentially kind of what's happening here, and you could think of that -7 as the y-intercept. So it says to write the linear function that corresponds to the nth term. Well, either way, so linear function, we're going to use function notation. So 2n minus 7. You also could have gotten that from here if you had 2n minus 1 minus 5, and I distribute, I get 2n minus 2 minus 5, which combine like terms, you get 2n minus 7. So either way, we can kind of get to the same answer, whether you use the 0th term or the first term. But again, linear function, that's going to really exist over this entire domain. Okay, negative infinity to positive infinity. All right, let's look at example 2. This is one kind of like what we did with the geometric. I don't think we had an example with the arithmetic like this. So we have to first, you can kind of figure out how you want to do it, but how many jumps you have. So 1, 2, 3, 4, 5, 6, 7. So there's 7 essentially jumps. Remember when I had the geometric, I divided them and then took whatever root it was of whatever the jumps are. In this case, I'm going to do -39, okay, minus 17. Okay, -39 minus 17. If you do that, -39 minus 17, that should, not 177. All right, that should give you -56. Okay, and I think we said we had 1, 2, 3, 4, 5, 6, 7 jumps. So we're going to divide by 7. Again, 2 things that are different here with arithmetic. If I'm given 2 terms, I subtract and then divide by the number of jumps. So you get -8 is the common difference. Okay, so that essentially means I could go through and I could subtract 8 every time. So I get 9, 1, -7, -15, -23, -31, -39. So I'm not going to write all out the domain and range, but the domain and range of the sequence would be all of the n values, 1, 2, 3, 4, 5, 6, 7, 8. The range of the sequence would be all of these y values. It's just happening at the y values. It's not happening anywhere in between. Okay. All right, so then if I look at example 3, okay, write a linear function whose domain is all real numbers that will contain the domain of the sequence. So same idea, we have a common difference of -8. We know at a sub 1, it equals 17. So there's many different ways to write this, but I'm going to write it in just function, not function notation first, just as a sequence. So that would be a sub n equals negative 8 n minus 1 plus 17. All right, and then if I wrote it in function notation, let's go ahead and do slope-intercept form. Negative 8n plus 8 plus 17. That gives me negative 8n plus 25. Okay, so this would be our final answer, but just so you can see that connection. All right, so again, let's do one more example with this arithmetic stuff. Let's go down to example number 5. I'm not going to go through all of part A. I'll write out the first couple, but we did do this back on the last one. This one is given in function notation, defined for the whole domain. All right, so let's just do the first, second, and third term. If I do the first term, it's 9 minus 3, 1 minus 4. So 9 minus 3 times negative 3. Okay, so that's 9 minus 3 times negative 3, which is 9 plus 9, which is 18. For the second term, plug in 2. Okay, that's 9 minus 3 times negative 2, which is 9 plus 6, which is 15. Okay, and hopefully now you see the pattern. If you didn't see it already right here, we are subtracting 3 every time, so then I know the third term would be 12. All right, I can use the same logic to find the 200th term. Substitute in 200 for n. So we have 9 minus 3 times 196. Okay, I make my box. So remember, I don't need 2 levels. So if you break that up into 100, 90, and 6 that we are multiplying by 3, we get 300, 270, and 18. And then you just add them all up. Again, you do not have to use this method. Sometimes it's a little bit faster if you were kind of going through it by hand, okay? So we have negative 3 times 200 minus 4, so that gives me 588. So we're doing 9 minus 588, which is the same as 588 minus 9, and then just make it negative. So I have 7, 18, 8, 7, and 5. So that should give me negative 500. 18 minus 9 is definitely 9. Negative 579. So obviously you keep getting more negative, okay? So that's where that negative 579 comes from. If I wanted to write this in slope-intercept form, 9 minus 3 n minus 4, I could just distribute, okay? 9 minus 3n plus 12, and I get negative 3n plus 21, and that's what's going on there. All right, so if we're looking at this, okay, now we can also do the same thing with the geometric sequence, okay? So, hold on, my alarm is going off. Oh, good. I know you guys were worried. Okay. All right. So what we're going to do now is do the same thing with the geometric sequence. Okay. So I'm going to find the common ratio r. I see right here I'm dividing by 2. We always write ratios in terms of what I'm multiplying by. So r would be 1/2. Let's just go ahead and fill this in. 16, 8, 2, and 1. And I can see that pattern there. So if I was going to write the explicit rule a sub n, that would be 64 times 1/2 to the n minus 1. Now, we are going to work on this more later, but I am going to show how this could look different. So 64 times 1/2 to the n minus 1, you're subtracting or adding essentially n plus negative 1. So I could break that up into 1/2 to the n, 1/2 to the negative 1. Because remember, when I multiply, I would add those exponents together. So I have 64 times 1/2 to the n, 1/2 to the negative 1. Okay, that's 1 to the negative 1 over 2 to the negative 1. Remember, whenever I have negative exponents, if it's negative on the top, it can go to the bottom and become positive. If it's negative on the bottom, it can go to the top. So I have 2 over 1. So this is the same thing as saying, so this would really be times 2. 64 times 2 is 128 times 1/2 to the n. And if we think about it, that should make sense because if I went backwards to kind of the 0th term, multiplied by 2, I would get that 128. Again, we'll talk more about that. I think that's in section 4 off the top of my head. Exponential function manipulation, but that's kind of also different ways I could write it. All right, so an exponential function. So we're going to write this as f of n equals 64 times 1/2 to the n minus 1. Again, exponential function is existing over the entire domain. Or we could say f of n equals 128 times 1/2 to the n. Okay. All right, so example number 9. Same idea as what we did in the last one, but remember this one is geometric. So the first thing I'm going to do is divide 36 over 144. Okay, you get 0.25 or 1/4. Okay, then we need to take the root of however many jumps this is. This is 2 jumps, so I'm going to take the square root. We can do this without a calculator. Square root of the top, square root of the bottom gives me 1/2. So my r here is 1/2. So I'm going to fill this in, 72, 18, 9, 9 over 2, and 9 over 4. Again, the domain would be all the n values. The a sub n, the range, is all the a sub n values, 144 to 9/4. If it's a sequence, it's discrete, it's occurring just at those values. If it's an exponential function that represents the sequence, it would be continuous and have the domain negative infinity to infinity. All right, we got two more in geometric. All right, go to example 12. All right, so write the first six terms of the sequence. So I'm just going to write the first 3 because I think most of us have the handle on this. So if I do 1, I'm going to substitute in 1 for n. So 6 times 1/2 to the 1 minus 1, which is 0. So the first term would be 6 because anything to the 0th power is 1. Now, I could do this a couple ways. I see my common ratio is 1/2, so I could just multiply 1/2 and get 3, and then get 3/2. Okay, but let's do it like this. 6 times 1/2 to the 2 minus 1, so 6 times 1/2 to the first. And then 6 times 1/2 to the second. So 6 times 1/2 squared is 6 times 1 squared over 2 squared, which gives me 6/4, which simplifies to 3/2. Okay. All right, so the a sub 0th term would be working backwards if I know the first term is 6. Okay. Couple ways to think about it. You could plug in 0 for n. Okay, if you get a negative exponent, it's really like multiplying then this by 2. So 6 times 1/2 to the 0 minus 1 equals 6 times 1/2 to the negative 1. We did one just like this. 1 to the negative 1 over 2 to the negative 1 is 6 times 2 to the first over 1 to the first, which ends up as 12. You could also think about it as if I go backwards, I know that if I'm moving to the left, I'm multiplying by 2, and 6 times 2 is 12. Exponential formula, same thing. It's just function notation existing over the entire domain. I'm going to write it like this, just so we can make this connection. If it was the 0th term that I was using, which is 12, my exponent would be n instead of n minus 1. Okay. All right, one more. We're just going to do one part of it. Example 14. So it says, Big Tech Electronics monthly payment plan. Buyers pay $50 at the end of the first month. $55 at the end of the second month. And $60.50 at the end of the third month. Okay. And so on for 1 year. What will the payments be at the 4th, 6th, and 10th months? Well, let's figure out what the ratio is. Okay. I can see it's obviously not arithmetic because I'm not adding the same number every time. So let's see if I do 55 divided by 50. I get 1.1. Let's see if the same thing holds for 60.50 divided by 55. And it does. So my 1.1 is my common ratio. So I would say a sub n equals 50 times 1.1 to the n minus 1. And I could find the 4th, 6th, and 10th months. So let's just find the 4th. So that would be when n is equal to 4. Oops. Did 2 steps in 1. 4 minus 1, which would give me 3. So in my calculator, I can do 50 times 1.1 to the 3rd power. And I get 66.55. And you could do the exact same thing for the 6 months and the 12 months, or 10 months, and I would encourage you to try that. Okay. So that wraps up arithmetic and geometric sequences and modeling those using linear and exponential functions. Remember, difference there is sequences are going to be discrete. They're going to occur typically at integers, doesn't have to be, but only at certain values. Whereas a function, if I'm doing function notation and I'm modeling them with linear and exponential, those will have a continuous domain from negative infinity to positive infinity. Okay, but they are going to follow the same patterns. All right, so hope you have a great rest of your day, and then we'll take a deeper look at exponential functions next time. Have a great day.